Hello everybody, welcome you all to this lecture series on electrical machines. In the part 1 we learnt about DC generators. In the part 2 today we are going to learn about DC motors. Let's just quickly recall what we learnt in DC generator. So in a DC generator you had a field winding in which you supplied some DC voltage which resulted in an current which is known as a field current, which resulted in a magnetic field, and then under the influence of that some current would be induced into the armature. This armature is being rotated by an DC or a diesel machine. Okay, so it is being run in a constant speed, so it induces an EMF into this armature, and then you connect a load. So there are two kind of things which we need to understand in DC generators. One is speed regulation and voltage regulation. Okay, so initially suppose I am driving this armature with the help of an diesel engine. The moment I increase any load, that will result in increased load currents, and increased load currents because there is a current flowing into the armature, it will also produce an magnetic field, and that magnetic field will oppose the magnetic field set up by the field. Okay, so these two magnetic fields will oppose each other, so it will become difficult for us to rotate this armature now because there are two fields which are opposing each other. So as you keep increasing the load, more current would flow into that load, and more current will induce greater opposing magnetic field in the armature, which is going to oppose the magnetic field. So the torque will increase. Okay, so to keep the RPM constant, you need to increase the fuel supply into the DC into the machine which is going to run this armature. So that is how the speed regulation is done. That is where the law of conservation of energy holds good. So more electrical energy being consumed, okay, that will increase the torque, and to maintain the speed you need to pump in more fuel. So the machine will run, the diesel engine will consume more fuel and burn more fuel, so that the energy law of conservation of energy is satisfied in this case. Okay, and the second was with the load regulation. So we saw that as you keep increasing the load, the loss IARA, that is the armature current into the armature resistance, that drop will increase. So slowly the terminal voltage will tend to drop. So if you have to do that, to compensate that, you need to somehow increase an field current which is proportional to the drop. So we have voltage regulation. That's how the voltage regulation is done. To maintain the constant voltage out here, we need to increase the current in the field. So these are the two things we studied in the DC generator. Now in the DC motor, things are very similar. Only thing is that here we are going to pump in electrical energy into the armature, and then that would cause this armature to rotate. So the input is electrical energy and the output is mechanical energy. Okay, so if you see this is the two permanent magnets placed here. Not permanent magnet, it is generally this magnet is formed by the field coils. Okay, so you have field currents going into these two poles, and then you have a magnetic field which is set up, and in which there is an armature, and in this case you are supplying the current into the armature through a split ring here. So once a current flows into this armature, so under the influence of this magnetic field, a force will be experienced by this coil, and that will rotate the coil. Okay, so what is important out here is the split ring out here, right? If there is no split ring, okay, assume this is a conductor, while it's in the bottom position, okay, it will experience a force towards the upside based on Fleming's left hand rule. So it will go up. So once it becomes vertical, now it has to experience a force and towards the downward direction. Only then it will rotate, right? So how can we do that? By using a split ring. So the split ring, what it does is, once it reaches the maximum position, vertical position, when it gets aligned to the field direction, it switches the direction of current. So now this conductor is going to experience a downward force, and the other or the opposite conductor is going to experience an upward force. So the split ring is very, very important here. When you have multiple poles, then a commutator. Okay, so that is how the direction of the current is changed in these conductors, so that it results in a circular motion of the coil. Right. So this is an animation which shows, okay, this is just the using a split ring. You have one coil which is rotating in and under the influence of the magnetic field. Right. Now here again, this thing is still elaborated. You have a current, it's shown in dot, and this is shown in cross. That dot indicates that the current is into the screen, right, and here it means it's coming out of the screen. Okay, so this is the plan view of the coil. Okay, so and then there is a field current which is going here. It is set up an horizontal magnetic field out here. So and then the motion is in the vertical axis. This is in the y-axis, the field is in the x-axis, and the current is in the z-axis out here. Okay, moving into the screen and out. So this is facing now because of the field which is in the x-axis, and the current which is coming and going into the screen here. It is experience an upward force, and this is experience a downward force. So as you keep moving, the coil will keep moving up. It will keep moving up. Again, it's experiencing a force. This conductor is experiencing excuse me, an upward force. This is experience a downward force. It will come up. Once it get aligned, the commutator will change the direction of the current. So now if you see, the direction of the current in this coil is now changed here and on here. So now this will experience a downward force, and this will experience an upward force. So it will continue to rotate like this. Okay. So now let's just take on some mathematical equations to get a better insight into what is happening. Okay, so now this is the external voltage which we have applied here. This is the armature resistance. Armature, I said, cannot have absolute zero resistance. It's a winding, copper winding. Although it is a copper winding, still it will have some finite armature resistance. So that is known as Ra. Okay, field, we are here we are assuming that the field is being separately given a constant voltage here. So field essentially remains constant. Okay, here. So we are not discussing about the field. We are just discussing what is happening in the armature. So this is the armature resistance, and this, as this coil rotates here. Okay, as the armature rotates here, because of the current in the armature, this is going to induce an voltage, because there is a field already available there, and then you are rotating this coil in that field. Okay, so it will generate an EMF within the coil. So that is known as the back EMF. Okay, so that is not this EMF. Okay, this is the voltage which we are applying. Because of this voltage, a current is flowing, and because of this current which is flowing in this, it is experiencing a force, and it is now rotating. That rotation is happening in a magnetic field which is there, right? So that now again, it's an, after all, it's an conductor which is rotating in a magnetic field. So there will be one EMF induced. Okay, and that EMF will oppose this EMF. Okay, like in the DC generator case, we said that there will be a field, the current in the armature will induce a field which will oppose the field which is already there. In this case, there is a voltage which we are applying here. Now it will induce one more voltage which will oppose the original voltage which is driving it. Okay, so it is similar. So you can compare these two philosophies. Okay, now you have one, this is known as the back EMF. Okay, this is the EMF which is caused because of the rotation of the armature in the field. So this is generally called EB. Okay, this is known as the back EMF. Okay, now the equation you can write, an armature E, the applied voltage, is equal to IA, the armature current, into the armature resistance, plus EB. Now I just multiply this equation with IA. Okay, let's see what happens. E into IA. So what is E into IA? It is, if you see from here, from the external power supply points, this is the voltage which I am applying, and this is the current which I am supplying, okay, into the motor. So from the source point of view, this is the power which I am consuming from the source, like voltage into current. So this becomes the power which I am. And what is I square RA? I square RA is the heat generated. Okay, you know the power of a resistance, I square R, that power which will be dissipated as heat. heat. So this is the heat which will get generated in the armature coil, that is the loss. Okay, this is purely, it's a loss, it is not useful to us. And what about IABE? What is this power? Okay, this is the mechanical power which is available to the motor to drive the load. So this is the mechanical power actually which is available for us to drive the load. So this is how an a DC motor works. Okay, this is the mechanical power, this is the loss, and this is the electrical power which is consumed from the source. Now I will just further go into some details of that. So this is known as power mechanical, IA into EB. Okay, now what is EB? EB is the back EMF generated. So that, you know, from the EMF equation which we studied in our last class for a generator, this is the flux, this is the number of conductors, this is the RPM in rotations per minute, this is the number of poles you have, and this is the number of parallel connections. Okay, that we saw it is different for lap winding and the other kind of winding. Okay, now this is EB. Okay, this is the equation of EB. Now if you have what is torque into the angular momentum, angular velocity. Torque into angular velocity is the mechanical energy, right? So like you have for a linear system, you have force into acceleration. Similarly for an angular system, you have torque into angular velocity. Okay, that you can relate it with the mechanical energy which is generated here, which we saw here. So IABE. And then for omega, which is the angular velocity, if I replace it with 2 pi n by 60, so if I do this substitution here, I will get the value of torque is phi z p ia by 2 pi a. So if you see here, the important thing which we have to learn from this equation is the torque is proportional to the armature current. Okay, so it is well understood, right? Torque is E is constant here. If you draw more current, you'll be able to give more torque. Okay, so torque is proportional to IA. So that is the thing which we learn from this equation. Okay, now let's take a shunt motor characteristics, wherein you have the field is connected in parallel to the armature out here, right? So I can write this terminal voltage as E into IARA. Okay, because this is the same equation which we saw the last time. And then if you write the E, okay, E is the back EMF which is induced. Okay, that you can write it as K phi AN. K is a proportionality constant, phi is the field which is generated. And now in this thing, in the shunt motors, the field is going to remain constant, right? It's not going to change, because this terminal voltage you are applying, you are going to apply a constant voltage out here, so the field will be constant. So the K and phi is going to be constant. So I can replace it with another constant called K1, and then N is the speed. So if I try to equate these things, if I write N is equal to V minus IARA by K1. So if you see, this is the steady state speed of an motor. So if you see, so if you put IA equal to 0 initially, as IA approaches 0, the speed will be V divided by K1, and then there will be, as you increase the IA, you will find a small drop in the speed. That is because of the drop in IARA. Okay, so this will be more clear in the very next slide. Okay, this shunt wound DC motors are known as they have the property of self regulation, right? Now here also we need to understand. Okay, now this is the DC motor, right? Here you are going to put the load. Okay, load is you are probably you are, say, if you are pulling up a lift. Okay, so more load means more number of persons in the lift. Okay, so that you are using more torque to pull it up, right? So or it could be some DC say motor which is driving an car or something. So if there is an upward slope, the torque will increase. Okay, so those are the torque. So let me go back to this slide. Okay, here. So now what happens when the torque increases? Okay, suppose for a shunt wound DC motor, if the torque is increased, so when the torque increases, so there will be what happens happens is naturally the torque produced by the motor is Tm, and TL is the torque due to the external load which is there. So momentarily, the moment the torque load because of the load increases, okay, that will be more than the torque which is produced by the motor. So the RPM will tend to fall. It will just tend to fall here. Okay, it will not fall, I'm just telling, it will tend to fall here. So the moment the RPM falls a little bit, okay, N falls, the back EMF also reduces, right? Because the back EMF is proportional to the rate of flux change in the coil. So since the RPM is falling now here, so EMF induced will also fall, so EMF will fall. So if EMF falls, the current in the armature increases, because what is the current equation? It is V minus IA RA. V is equal to, okay, the equation is IA RA and plus E. Plus E, right? So the back EMF, if it reduces, the IA increases, because the opposing voltage is reducing here. So IA increases. If IA increases, the torque of the motor increases, right? Because the torque, we said, it is proportional to IA. So the torque generated by the motor increases. Now this will try to match with the requirement, or the torque requirement, okay, which is the load torque. Okay, it will try to match up with that, and then the speed will be maintained here. So this is known as the self regulation. Okay, let me just explain you once more, so that this is very important concept of a shunt wound DC motor. Okay, when the torque increases means the load, okay, which you have connected. So because the load on the motor increases, the RPM decreases. A decrease in RPM will result in decrease in back EMF, and decrease in back EMF will increase the armature current, because back EMF is opposing the input voltage. So now if the opposing voltage is lesser, the armature current will increase. Okay, if that is clear from this equation, right? Here, or let me go one back here. So if this decreases here, okay, this is constant, so IA has to increase. Okay, so now here IA increases. If now IA increases, the torque increases. If the torque increases, the RPM will be maintained. So if you see, this is the torque speed characteristics, this is the torque. If the torque is increasing here, okay, the speed will, the dotted line shows it is an ideal condition, it will continue to remain same, but there will be a small change in this thing because of the other losses which are associated, okay, RA. So that it will, but more or less the speed remains constant. So this is known as the self regulation, and this is torque and IA characteristics, that we have seen that torque is directly proportional to IA, it will keep increasing. Okay, so that is why DC motors, shunt wound DC motors, is one of a very good motor if your requirement is of constant speed. Okay, and now obviously more torque has been generated, that means more energy is required now, and that energy comes by consuming more current. Okay, because IA will increase, so V into IA, so the power, more power will be obviously be consumed from the source which is driving this motor. So more power is being consumed and more power is being delivered here, whereas the speed is kept constant here, right? Okay, the same thing happens in the reverse direction also. If there is a decrease in torque for some reason, suppose you are coming down slope here, or somebody has jumped out of the lift, okay, where now the total load requirement is less, then the RPM will tend to increase, and this will increase EB, that will decrease IA, and that will decrease torque, and then the speed will be maintained in that case again. So that is how. Now in the shunt wound DC motors, it is slightly, in the series wound DC motors, the things are slightly different out here. So here what happens, suppose the load torque increases here. Okay, what happened, the N, and that is the speed, tends to come down. Okay, the back EMF tends to come down, so the armature current increases. Now here, since it is a series wound, okay, the field current also increases, okay, because it is the same. Okay, armature current is same as the field current. So field current, if it increases, it also increases the flux, and that flux will increase that EB, right, that is the back EMF. So armature current will not increase in this case. Okay, that is why, so the torque will not increase. So it will now go and stabilize at a lower RPM, because there is no now the load current and the torque of the motor, and they don't match automatically, unlike an shunt wound DC motor. So here the armature current will slightly come down. So that is why you will find that here, if you see torque versus speed graph, so as the torque increases, the speed will decrease. This happens in a series wound motor, right? So this is the problem. Here the torque goes as an it's not linear out here, because if you increase the current, two things happen, right? Here in here, because the field also increases, okay, along with the current. Here, there we assume the flux to be constant, that's why we got a linear relation between the current and the torque. Here not only that, the field also increases with the current, so that is why this is an hyperbola out here, right? It is going to increase by square. It is dependent on I square, okay, not purely I. So these are the two graphs which are applicable to the series wound DC motors. Okay, now if you have separately excited DC motors, this is generally where you are applying the field current separately through a diode rectifier, and this is a controlled rectifier, right? So these are the, so you can use this kind of configuration wherever you want to control the speed of the DC motor. Okay, so either you can increase the voltage which is applied to the armature coil to increase the speed, or you can decrease the field currents to increase the speed. Now decrease in field current, as we know, I just explained to you, a decrease in field current generally in this case increases the speed, because what happens is it reduces the back EMF by reducing the field. So that will increase the IA, and that is why you will have because IA torque is proportional to IA. So if you reduce the field current, so the back EMF reduces in this case. So that is why you will get that increased speed, or you can just increase the terminal voltage, armature current out here, and you will get it. So this is generally used, this configuration, where you need to control the speed of an DC motor, right? Now starting of a DC motor. Okay, so what happens is, when you are starting, initially when you apply a terminal voltage, there is no back EMF because the motor is not yet started rotating, right? So if you do that, so there will be huge current which will flow into the armature current, which can damage the coil of the armature current. Okay, so that is why while you are starting the armature, when you are starting it, then you need to give a series resistance, an external resistance, in series to the armature, and then you can remove it after the motor has started running and started generating an EMF, back EMF. Okay, otherwise there is a tendency to, and there is also a requirement of no volt release coil and over load release coil. I'll just explain you this with a diagram in the very next slide. Okay, so we have several kinds of starters which are there for the for the starting of DC motors. I'll explain two of them, 3-point starter and 4-point starter. And so let's see how it works here. So this is the DC supply voltage which is available. This is the switch to switch on the motor. Okay, so this bar and then what is shown on top forms the starter. So this is the field coil of the motor, and this is the armature of the motor, armature coil, right? So negative you are supplying it to the field, and also you are connecting it to the armature, and positive you are going to give it through the starter. So let's see how the positive is reaching the field and the armature. Okay, so from the field it's coming here, right? There is an overload coil out here. Okay, assuming this connection is off initially. Okay, so this lever will get pulled up only when there is an overload current. So we are assuming presently when we are starting there is no overload current, so this lever is in the down position and this contact is not made. Okay, so the current will come here, and then this is a lever. Okay, so this is a lever, this initially remains in the off position. Okay, so off position means it will remain at 1 out here, right? So the current will, the positive voltage will come here through this lever, through 1. Okay, through 1, it is going to have through this path, it is going to come here. Okay, it is going to energize this coil. Okay, this is a coil which will energize this coil and the field winding, it will come to the field winding. So now you see one path which is available from the positive. It is going to come through this coil, through this rod, through this point 1 here, it bypasses, it comes out here through this coil and through the field. So the field will start getting a current, and in the field current you will find a full voltage being applied to the field coil now here. Okay, what about the armature part? Okay, let's see. So now this voltage is coming from here through this coil here, through this rod here, through resist to point 1 here, and then through resistance R1, R2, R3, R4, R5, it comes here and it comes to the armature. So the moment you are switching on, two things is happening. You are giving full voltage to the field, and you are giving and a series resistance consisting of R1, R2, R3, R4, R5 to the armature. Okay, so there will be no short circuit current in the armature because you are put a large resistance in series with the armature, and also initially there will be a requirement of huge torque, right? So that is why you are applying full voltage to the field coil also. Okay, now what happens is, now you are also supplying the field current through this coil. So now this coil will attract this lever towards itself. So this rod will start moving from 1, 2, 3, 4, 5, and it will come to the run position. So as this rod is moving out here, what happens? If you see here, what happens is the current what happens to the armature? Okay, so the current is coming from the positive out here through this coil, through this rod. Now instead of 1, okay, this rod moves and makes an connection at 2 out here, right? So now R2, R3, R4 and R5, the current is going to R2. As this rod keeps moving from 2 to 3, 4 to 5, and it comes to the run position, finally after some time the power supply available will be through here, through this coil, through this rod, through the run position and armature. So the entire voltage is available into the armature. What happens to the field? So what happens to the field? If you see, it is going from here to this rod. Okay, this has come to the run position out here. Now from the run position, through these resistances, it goes out here through this coil, it has come to the field position. So what has happened, by this coil getting energized and pulling this rod here, okay, after some time when it reaches the run position, after a few seconds or something, what happens is the resistance, the full voltage is now 1, it reaches the run position, full voltage is applied across the armature, and then in the field in series this resistance, the field current is now, because it is already started, you don't require that kind of torque, so the field coil current is reduced and the armature current is getting the full voltage here. So that's how it comes to the run position. So this is how it is, this starting is ensured in a smooth manner without any excessive currents in the armature. Now there is something, so this is known as the no voltage coil. Okay, because when it holds it here, okay, as long as there is a voltage available in the field coil, okay, as long as there is a voltage applied here, this relay will be energized here. Okay, it will be energized here and it will keep this bar at this position. Okay, the moment you are cutting off this power supply, this will get de-energized. Okay, this coil will get de-energized and it will release this rod. So this rod will come back to its original position out here, and it will again will be ready for the next start. Okay, so that is why this is known as the no voltage coil. So the moment you are cutting off the supply, this will come back here. Okay, this will release this because there is a spring attached to this rod. So the natural position of this rod is going to be at this position. Okay, only when this coil is energized, this will come to this position. So that is why it is known as no voltage coil. So the moment you are cutting off the supply, this will come back here and it will be ready for the next start. Okay, now there is one more relay which is known as the overload release. Here there is one more coil here. Now suppose for any reason there is an excessive current going into the armature, this relay will energize. Okay, so this relay, once this gets energized, these two contacts, they will be made, this contact. Okay, so what is these two contacts? They are parallel to this coil, right? So they are parallel to this coil. So that means the input and output for this coil will get shorted if this relay gets energized. So that if the input and output get shorted, there will be no potential across this coil, right? So this will get de-energized and this bar will come to the off position. Okay, so that is how it prevents excessive current. So in case there is an excessive current, this contact will be energized here. That will short circuit the input and output of this no voltage coil, and that will release this bar. Okay, so that the motor will get switched off. That's why it protects the motor from heavy currents. Now if I go back, there is some drawback of a 3-point starter. Generally what we do is we regulate the field current to control the motor speed. Okay, so it's not, so you have to connect an rheostat in series with the field coil. So once we adjust the rheostats, there will be, in some cases we need to reduce the field currents. Okay, if you reduce the field currents, what happens is the coil current in this coil will also reduce drastically. Okay, and that will release this lever. So it is not a very good idea to connect this particular relay in series with the field coil. So that is why you have a slight modification of a 3-point starter, which is known as an 4-point starter. This works exactly similar to the 3-point starter. The only modification done out here is there is a resistance which is connected in series with this coil. So that is made the current flowing in this coil, no voltage coil, is made independent of the field, and the field is made independent. You can connect an rheostat here. So the field is taken from here, from the run point. Armature is also taken from the run point, and you have put a rheostat out here, and from here you will see a fixed resistance is put into this coil, so that you change the current in the field coil, that is not going to affect the functioning of this no voltage coil. Okay, so with that I think I have covered most of the points which are important with respect to the DC motors. In the next lecture I will talk about AC generators, and then we'll move on to AC motors. Okay, thanks a lot.